next speaker will be Malith Jayasinghe. He's the head of research and artificial intelligence at WSO2, and he gives a talk on using AI for performance feedback and data programming.
Thank you. Can you hear me?
Yeah.
Hello everyone, hope you have been keeping well. My name is Malith Jayasinghe. I am the head of research at WSO2. So today I am going to be talking about an interesting project that we have been working on for some time. So we put a lot of effort into this, and now this is actually now a part of Choreo. It's available as a feature. Right? So I won't be going into the details of Choreo, but I will talk, like say, for 5 minutes about Choreo and then try to sort of establish the link of this feature to Choreo, and then after that it's all the details like how we model it and so on. Right. So think of you are an organization and you are trying to build a product or a solution. Right. So basically for your customers, you want to solve a particular problem or set of problems for your customers. Now when you do that, as Srinath mentioned, one of the important things is to basically provide that unique digital experience. Right? So it is this digital experience that will give you the differentiation and hence give you that competitive advantage. Right? Now, so when you are building such a product, the first thing you do is you take a look at the technology stack. Right? So this is actually fairly complex. You need to figure out which vendors to deal with, what sort of APIs to use, what sort of teams to hire, what sort of training to provide to them, and so on. Right? So what you would realize is that developers are spending a lot of time basically writing the code which is not part of the core function. Right? As you have seen in this figure. So this is the application life cycle. So in each of these stages you have to do certain things, but the actual core functionality, which is the development of that core functionality which gives you that differentiation, basically developers are spending less time on that. Right? So this is where Choreo comes in. So the Choreo is that digital platform as a service which will allow you to basically build this product or the solution. It's simply that. So the Choreo has the right set of abstractions, right? And it does have also the best practices built into it. So which will allow you to accomplish this task. Right. So when you have Choreo, now what happens is you can focus more on developing that core functionality. Right. So this particular feature or the idea which I am going to be talking about is related to that development section. Right. So basically it will allow you to do that more efficiently by trying to give you performance estimates or performance forecast in development time. You don't need to deploy and run it to see the performance numbers. Right. Okay, so what do we mean by API programs here? So basically we see two categories of API programs that are happening. So the first one is basically an API integration or an automation we call it. So we basically create an integration application using a set of APIs. So an example for that one is, say for example, when a GitHub issue is assigned to you, you want an SMS to be sent, you want an email. Right? So this is the first type of API programs that you can write. And the second type is the API composition. So here you actually compose, you basically write a service by composing using set of APIs, and then you expose it for others to use. Expose it as an API for others to use. Right? So this particular methodology or the model that I am trying to propose is relates to more to this second one. Right? So this is the type of service where you will get significant amount of traffic. Right. So the use case is the same as what Srinath was talking about. So it is. So I'm not going to the details of this because Srinath has already presented. We basically want to write a service that is capable of computing COVID-19 cases per million people in a specific country. Right. That is the use case that I'm going to be focusing on, and then we will see how to model this, and then how to forecast the performance for this use case. Right? So as you can see, so in this use case, as Srinath mentioned earlier, there is two connectors involved. Right? So the connector is used whenever you want to make an external call. Right? This is a service, you are writing the call and then you want to talk to a different endpoint. So you have to create a connector. So in this case, first you make the call to the COVID-19 endpoint and you get the number of COVID-19 cases in that particular country. Of course, you will have to pass the country code. Right? And then you have to make another call to get the population in that country. So that is the second call that you do to get the population, and then you basically divide the total number of cases by the population, and then you compute the COVID-19 cases per million people in that particular country, and then you return the result to the caller. Right. So this is the code. Srinath has already shown this, so I'm not going to go to the details of this. Right. So a little bit about performance. So you need to understand why we are trying to do this. So performance, as you know, is one of the most important non-functional requirements. It plays a very important role. Right. So it has a direct impact on the user experience in these sort of systems. Right. So the poor performance can cause customer dissatisfaction, and it can even lead to churn. You might lose customers because the performance is not good enough or it is performing poor. So these services or the API that we are talking about, they are handling large number of requests. There are two main things that impact the performance. Right? So the first thing is, of course, the characteristics of the incoming workload. So here we are talking about the arrival rate, the inter-arrival time distribution, the concurrency, the message size, and so on. Right? The second thing is the characteristics of the program itself. Right? So you have the incoming workload characteristics and the program. This is what decides what the performance is. So these sort of API, these sort of services that we are trying to model, one of the things that affects the performance the most is this network calls. And so these are very much network bound applications. So when you make a network call, basically it will add significant latency to that program, and therefore the total time will increase. As a result, it will affect the throughput and all the other metrics. So in the first version of this model, we are taking into consideration only the network cost of network calls, the external interactions. And in fact, if you take a look at these API programs, there is not a lot of processing that happen in the service itself. You talk to one point, and then you get the results, and then you do a little bit of processing, and then you make a call to another point, right? So what's the benefit of this? So of course, performance estimates, if you can estimate the performance, then there are cases where you have service level agreements, right? So when you have these performance numbers for the results, you can actually check these service level agreements are met, provided that these ones are accurate. Right? So that is one use of this. And also you can avoid bugs. The example that Srinath pointed out, say for example you are holding a particular endpoint multiple times accidentally. Right? So you would immediately see that there's a degradation in the performance at the development time itself. Right? Also, this will allow you to understand the scalability properties. As the load increases, how does the throughput and the latency vary? Also, to at least to some extent, this could save developers time and save resources, because you can minimize the number of performance tests that you have to do. Right. Okay, so now we are talking about scenario. You have a service which is making API calls. You want to estimate the performance. So what is the performance that we are talking about here? So mainly there are two performance metrics. The first one is the throughput, right? So the throughput is the rate at which a service or a server is processing requests, right? So this is a well-known curve. So this shows how the throughput varies with the load or the number of users. It increases linearly, right, in the initial phases, then it sort of stagnates for a while, and then it starts to degrade. This is the usual sort of a pattern that we see. When it starts degrading, you call that the system is not in the steady state. It has gone out of the steady state. The other performance metric is the latency, right? So the latency, the definition of the latency could differ depending on the context. It's actually a measure of waiting. Right? So in the context of services that we are talking about, it may be, for example, the round trip time. Right? So the latency actually, it's not, it's a single value, but if you do a performance test, you get a lot of latency values. So latency actually exists in a form of a distribution. So as you can see here. So for each performance test, if you run a performance test for a particular number of users, you get a latency distribution. So these distributions are typically skewed distributions, right? And it can even be very long tail distributions, depending on the workload characteristics, right? So from this latency distribution, then you can derive certain statistics, such as the average latency, 99th percentile latency, and so on, right? So this figure shows how the latency or the average latency or the 99th percentile sort of varies with the load. Again, we see a linear increase, and then it starts to increase faster, and then it starts increasing exponentially. Right. Okay. So our objective is to see whether one of the objectives is to see if you can basically get the throughput and latency curves for this service which we have written. Right. So that's one objective. So then you can understand the scalability behavior. The second objective is to see whether you can get the latency breakdown. Once you select a particular number of users, say for example 20 users, what is the breakdown of this latency between these network calls? Right. So how do you do this? So what we have done is we have represented this service as a queuing model. So the queuing theory is one of the ways to model the computer system's performance. Right? So in this case, we are representing it as a closed queuing system. Each component in this service we represent it as a server. So the server consists of a queue and a processing element. You can see a queue and a processing element, right? So you can see there's the workload generator here. So the workload generator will generate request, and then you have the application, which is the service that you write. It is the code, which is this on the left hand side. This is what we write in code, right? And then you have the external API, which we also model as a server. So that one in this case would be the COVID-19 endpoint. Then you have the World Bank, right? So there are 5 servers involved. So the request flow here is that first the workload generator generates a request, right? Or it can be client, and then it will send to the the service. Then it will make a call to the COVID-19 one. So that is number 2, and then it sends the response back. Number 3. Then it does another call. Number 4. That's the World Bank, right? And then you get the response back. And then the final result is sent back to the client. That is number 6. So this is the representation of this service, which is a QE model. This is how we model this. Right. So then, how do you actually get the performance for this? So this is a 2-step process. First step is to basically build a set of models for each of these interactions, right? So in this case we have 2 models, and then once using those models you solve for the full system, and then you get the performance for the overall system, right? I hope that those 2 steps are clear. First we model the individual API's performance, and then we basically solve a set of equations which is based on the Little's law. We write set of equations and there's a solver involved. Using that you can get the performance for the overall service, right? Right. So let's talk about the first step now. So this is modeling the individual endpoints. So what is the data that we need to collect here? So right now we are collecting 2 things. The first one is the number of requests in progress and the latency of request for that particular interaction, right? So for the COVID-19 case, you can measure the latency and the number of requests in progress, right? So this connector does not have to be used in this use case.
But Malith, didn't you get only the request out of this integration?
Sorry?
Isn't it true that you only get the number of requests of this particular integration? There may be other applications that send messages to the COVID-19 client.
So actually that we don't consider right now.
That's what I think. Okay.
Yeah. So what
it's out of this application.
Towards the end I will show you the comparison.
Yeah.
So there we will notice that basically that has a minimal impact right now, at least for some reason.
Okay.
Yeah. So this is the initial. That's why I said this is the initial one.
Thanks.
Right?
Thanks.
Yeah. So basically now we have. So what happens is now this is a ballerina program, right? So the ballerina has built-in observability. So and this is running in Choreo. So when this is running in Choreo, it will the program gets instrumented automatically. Users don't need to have to worry about these things, and this information gets collected. I will show you the architecture for this later, and then basically we will store that information. Right. So this is a data set. So by the way, this work in progress is represents the load. So this is the latency for a particular endpoint. So as you can see, we are seeing that pattern which I have explained earlier. Now in this particular case, for this we have actually fitted this model called USL, Universal Log Scalability. So that actually describes how it scales. So basically the one advantage of using analytical model here is that this is a domain model, right? It knows the scalability. Like if you use a machine learning model, initially we have tried machine learning models also, but if you have outliers and all that, basically you can get into problems. So this is the analytical. So again, still we are talking about modeling those external API. So we haven't got to the other part yet, right? So these are the patterns that we are seeing. So this is one pattern. So this is what we see for most of the APIs, right? So clearly an increasing trend as the load increases, the latency increases. Then we are seeing this sort of a pattern also. So this is so basically in this case there are some missing values. What that means is like when users are accessing, but the number of users is sort of only in particular regions. So these must be the performance tests or something. So this is another pattern which we have seen when we analyze the data. So one thing we try to do is that you can do a Bayesian fit, right, to the data. So the earlier one which I mentioned, the USL is just an analytical model. You just try to fit it, you try to force the data into a particular curve, but you don't have to do that. You can even do something like a Bayesian fit. So then as you can see in those areas where there is missing data, especially in this case, you will see that there is very high uncertainty in the predictions. So one problem we are trying to do is that in those areas we can use an analytical model where there is high uncertainty. So the analytical model knows how to interpolate between the points, and in the other areas where there is a lot of data, we can use machine learning models, right? So it's kind of a hybrid approach.
The pattern that you observe, is that only for the COVID-19 API, or is that what you observed in many different?
For multiple.
For multiple, okay,
yeah.
Interesting.
Yeah. So that hybrid approach actually improves the prediction accuracy, right? Okay, so this is another pattern we have seen. Now, so what happens is this case is that so the first request had a higher latency and the subsequent ones had a lower latency because the endpoint actually cached the results and returned the cached result. Right. Okay, so this is the data collection architecture for this. So which is we have in Crete. So you have each of these apps or the integrations or the services deployed. They are instrumented. So while they are running in production, we collect this data and then you put it into some message queue, and then you go and persist this. So it says it's a training data. It's actually the everything. You will use subset of training data to train the machine learning models. So this is the observability platform. So there's a trainer, the model trainer, which will periodically pull data from this database and then train those models, right? And then we have a model store. So that is the training pipeline, and then of course, now we will talk about this. You have now set of models. You need to now, so this is what happens when the user is actually coding, right? I'm writing a program, then I want to estimate the performance, then there's this estimator service. It will send the request to that service. So this is the inference flow. It will basically pull the models that are required and then do some computations and then return the results, which is the performance estimate. Okay, so let's try to understand what happens there. So here what we have to do is, to get the performance estimates for the service, you have to actually parse the program. You need to understand what sort of connectors are there, right? You can't just get the performance just like that. And if you have a for loop, which is calling a connector multiple times, then you need to know that there's a for loop. So what we do is now for Ballerina, you can simply write a parser, which will go and parse this program. So this is called the AC, right? Abstract syntax tree of the Ballerina program. Right? So it will basically extract those features, which we will basically send it to the backend. Right? So then once the backend, which is the performance estimator service, basically it will then it will detect that this particular program has these APIs, and then it will then pull those models, and then it will do the final calculation by solving those system level equations, which is based on the Little's law. Right? So here the one thing is that we are not making any assumptions. We don't have the Markovian assumption here. So we don't assume exponential service times or anything. We just do the black box modeling for the backend APIs, and then we solve the entire system using the solver. Right? Giving theoretic solver. Right, so let me now try to show you this in action. Okay. Right. So when you first come to Choreo, what you notice is that this estimate, so this is the overall estimate, it is showing the performance forecast from concurrency 1 to 25. And the latency is 61 milliseconds to 2.13 seconds, and similarly for the throughput range. So you can't show this for all the programs, so it depends on the availability of data. Right. So because some programs may not have enough data to give you an estimate for range of concurrencies. Right. So then if you want to know more, we can click on this.
Well, that's fine. Malith, how often do you retrain?
Actually, earlier we had it configured for, we had it configured every 1 hour.
Oh, okay.
Actually, that is not required, so we can even retrain, on a daily basis.
Sure.
Or something. Sure. Yeah. But there is lot of problems like which we need to solve in the ML ops area. This becomes, you will have to do the model version controlling, and then the observability, AI, check for data drifts, concepts drift. So that is one problem that we are working on at the moment.
Thank you.
I think it's coming. Okay. So these are the curves which I was talking about. So here, so this is how throughput and latency, vary with the user count, right? So what you can do here is basically then the other thing is that you can click on a particular point and you can see how these numbers are changing. So for some reason in this particular case, it's actually the throughput is not increasing. It's in that other region, something is becoming a bottleneck and basically throughput is degrading. That is what the model is saying. So also here, if you go to the code, let me close this. So in the code itself, you can see these performance estimates as well. Not sure it is clear enough. Right? You can see the breakdown there. Okay, so let's get to the presentation now. Let's wait it. Okay, I want to talk a bit about how do we evaluate the accuracy of this, right? Because we have a model which is capable of providing performance estimates. Now you want to evaluate its accuracy. So we have actually tried out two methods. First is the discrete event simulation. So discrete event simulation can basically simulate any stochastic system or Kiving network. So the simulator code is that before you can take a look at it. We have a simulator that can actually simulate a time sharing server and also it has the thread level abstraction. So we are not just simulating the first come first serve server, which is quite straightforward, right? We want the ability to control the thread pool sizes, the context switch overhead, and so on. So then we take this one and basically then you can build your simulation model using that server and then you can generate the traffic, right? You give, okay, what are the, you can basically give different distributions and then run a simulation and then also you can get the results using the model as well, and then you can compare. The second testing, of course, is the testing it in the real system, which is Crete, right? You will have to do that as well. So for that, we, you have to test it in the real system. You have to generate some data, and then you compare it with the results returned by the model. So this is the same use case like which I have been talking about, but the backends are sort of implemented in the simulator. So I mean, for this you can use something like Omnet, or there was another one named the Python. I can't remember the name. Right. So then you have to give what the average processing times are, right, and the number of cores, thread pool sizes, and so on. So this is the comparison of the simulation results and the results returned by the model. Right? So this is the throughput versus concurrency curve, and then similarly you have the latency versus concurrency curve. So
do you use that, Malith, in order to predict, for example, the thread pool size?
Sorry?
Can you use that to predict, for example, some of the hyperparameters, how to set the thread pool size?
Thread pool size?
Yeah.
No, we don't do that at the moment.
You just play around with it? Okay.
Yeah.
Thank you.
That is something you can do actually. Yeah. Okay, so then the second thing is testing it using the real system data. Now remember, this is a development time user experience, right? The user actually hasn't implemented the use case and run it yet. So what we do is, individually you have to populate those backends. This is the thing that you need to understand. You have these backend services. You basically generate the data, and then when the updater runs, it will basically go and create the model for that backend, and then you do that for the second backend, and so on. Right? And then you come and write your service. Then you see the performance estimate, but you have not run the use case yet. So that design time, what you get at the design time, or what the estimator returns, to verify it, then basically do a test. You compare with that one with the model result. So there's two types of things that we can compare with. One is the observability. So this is what the platform actually shows you, the Corio's observability data. You can compare that with that, and also the JMeter. So JMeter is the client here. That is the client side. So these are the these are the results that we are getting. I mean, we have a lot of such plots. I'm just showing one of those. But by the way, so in this particular case, we are populating across all concurrencies. So if you have regions where there is missing data and all that, then the accuracy might not be this good. And here, remember, we are using analytical models to model the backend APIs, not that Bayesian the approach which we are currently working on, right? All right. So this will bring us to the end of this presentation. So basically, we have made an effort to estimate the performance of a service or an API which basically has multiple API backend calls, right, in the design time. So this we believe will be quite useful. By the way, we are writing a paper also, so the paper is in its final stages. We haven't submitted it yet. So anyway, we have been published quite extensively in this performance area, this particular theme. But this is one of the quite advanced piece of work which we have done recently. So this will help basically in multiple ways. The first one is ensuring SLAs and then avoid performance related bugs, understanding the scalability behaviors, and so on. The overall system is modeled using a Kiving network, and then we use black box modeling for backend APIs. Right? We didn't try to go. So basically, it's a very high level modeling. You know what the latency is, you know what the number of users are, and then you basically use an analytical model or machine learning model, and then you solve for the entire system and get the performance results. Right. So that is the end of the presentation. I think it's time for the questions. I hope it's good.
Are there any questions?
I have one question regarding performance estimates. You say I have 60 milliseconds processing time for my overall application I built and with the backend integration. What about having different deployment targets? So small virtual machine versus full-fledged Xeon server. How to apply this? So it's huge difference having a.
It's a good question. So right now, so are you talking about? So right now we assume this service which is deployed in Kotlin is not the bottleneck. It's not the bottleneck. So the cost of performance is coming from those external
Okay, then my follow-up question would be, what if I decide as a customer to change the deployment target of my backend services? So I decide has two less resources, and I decide to double.
Yeah, so what will happen is then the model will, so there's going to be new data coming, right? So if you go and say, for example, your backend service is 2 cores, now you are basically upgrading to 4 cores, right? So the initial estimate would be for whatever the data is available. But if you go and then change, upgrade it, the second time it runs, then you would expect the latency to be low, right?
Yeah, but then I have no historical data in choosing.
Yes. Okay, that is, so this is the problem that I was talking about. So in that case, of course, is there a way to detect it?
So, I mean, that way. So, the way I looked at this, so it depends on whether I kind of step out of the problem this way. Basically, the use case is that there are APIs. Right? There are APIs in the cloud that we are integrating. What they run on, we don't have control. It's Salesforce API, they give us a kind of SLA, end of the story, right? So we are integrating. Now, of course, with now we switch. So basically, when we look at that, basically we get SLA. So we use that SLA information. So in this case, there is the fact that whether they use a different hardware, etc., we don't look at, right? And the other side is that what this forecast is trying to do is give a kind of an upper bound of what if I am integrating these Power APIs that include this SLA, etc., and then give you a number. So and then I would argue. So actually I was fighting for the most simple solution, and then like we can try to do more. So the thing is, I would even go up to the argument that the simple variation is okay because this is the feedback, right? It's like if you put the API inside the volume, bad idea, right? So because the 20%, 30% change won't affect because if you do something significant and code level wrong, it will just go off the screen. But then you can start at that level and then try to add details step by step.
So I guess the answer to the question is the estimate would be incorrect in that case.
No, but I will argue it's okay.
Yeah, so the immediate answer.
Yeah.
Because the system hasn't seen that yet.
Yes, that's a big issue when forecasting or predicting overall latency of your system, and you have backend services which are 80% of the latency, and it's more obvious to change them than your
So actually the other thing is the granularity, right? So right now we are really looking at this in progress because there can be different other things other than that we can capture. And when you basically build that model, you can incorporate those as features.
That's an excellent discussion for a coffee break.
Yeah.
One other question? No? So we reconvene at 10 minutes to noon. Yeah? Thank you. Bye.